What is?
The
Do you want to keep that one?
very small little. Yeah. Looking around.
Ta-da.
Saying hello. Come here, Mom.
Alright, so we're running and giving you guys your maps.
Come
So you had the 1,000 year map, didn't you, right? So this right here is 1,000 years. There you
Like
go.
up, I know, no COVID.
This one
No COVID.
is 100,
No.
you had 100, right?
That's more.
There's your 100 years.
Oh.
And 50 years. Where's Yusuf?
Is California really green?
Yusuf,
So
come
we
here.
put yellow like gold.
This is your.
It's
California
so
gold
green.
rush.
California's the greenest.
It is very green, that's true.
Yeah.
But I was inspired with the gold rush.
Yeah.
You said that so serious.
I'm so sick.
Oh, yeah, both.
Inspired by the gold rush, how dare you?
They doing? You look at them.
Don't look at me, look at him.
Don't look at me.
No,
Are you-
look at him.
If you do, then come on in and everybody come sit down so we can all kind of see and hear each other. All right. That's about everybody. Who's hiding around the corner? Chloe, you are as hiding. Come down. Can't see you over there. There's plenty of room over here. Plenty of room. Look, empty space in this room.
Oh, it does say.
Oh.
That's interesting. You can see that.
Yusuf, go where your team is. Everybody else squish in. All right, we're good.
The water's fine.
That's a good fella. You can sit right there. You look very happy there.
It does say brown or green. I didn't
Yeah.
notice that.
That's okay.
We took inspiration from the gold.
Let it be. It's all good.
Please.
Oh my
I thought
gosh.
since Alex wasn't here, we were scared to say one thing. No, it's not.
Not gonna die. You don't have 9 pillows.
I think he might. I think he really,
Yeah.
truly
I know.
might.
All his fans.
Scott, you got a place to sit? Are you comfy? You're good?
I
All right, you're good.
I'm Danny from class here. Just square spots.
Oh, we're just chatting at the moment.
Area so what?
No, you're not working now. No, I had you work. You worked just fine the other day.
We
Yeah.
did too far. Many times.
Everybody has a map.
We did.
Y'all are killing me.
We did. Well.
Yeah. Oh.
Gotta make sure it's not. All right,
Yeah.
so did anybody have? Okay, everybody has formats, formats, right? Everybody did get that done.
Yes.
Good. Okay, cool. All right, so let's chat a bit. Let's look at stuff. All right, so you should have been able to find your plates here. Now, some of these are extras that we didn't talk about today, but you can see where the Pacific plate is. Ouch! Oh, man.
We were just so excited about Judge.
I know, I know.
Judy.
Oh,
Put
is it
out
Judge
that.
Judy? The best, the best.
The
Hold on
best
here.
of the best.
Actually, it was Judy Justice.
It
Oh,
was
is that new?
Justice.
That's new. I don't know that then.
only on.
Judy
Freevee,
Justice.
In case you're wondering, only on.
Mhm.
Let's do your-
Amazing.
Very
All right, gonna be up in just 1 second.
Queen Elizabeth jumped out of an airplane.
That's true.
Y'all are so funny with that. We all loved it though. It was amazing. Why are we having trouble
connecting? The idea.
I know.
Amazing.
Such a good sport though. I mean, she
She was in
truly,
Paddington.
Yeah.
She's a great.
she's a great sport. I truly love. I was very sad when we lost her because she's very cool. All right, let's go back to, okay, catch up cursor. There we are. All right, now we're good, right? Okay, so you can see we have this gigantic Pacific plate and it's moving that direction.
The biggest plane.
And then we have the North American plate moving that direction. And then down below here, over in like the bottom southern part of Mexico, you've got a Cocos plate going that way, a Caribbean plate going that way. So it's getting squashed, right? And then you have this little Juan de Fuca plate, poor thing, stuck in the middle of this, right? This kind of action. So if you found all those, the 3 plates that you were supposed to label, that should be pretty clear. All right, so now let's talk for a minute. We talked about which way the plates were moving. So what direction is with consideration of the Pacific plate, what direction is the North American plate moving? Okay, Drew, you go.
moving south.
Is it south?
Southeast.
Everybody agree south, southeast, generally to the south? Okay. So that means what direction is California moving in comparison to the rest of the country?
Up, down.
Which way? Give me a cardinal direction, Piper.
North.
North, northwest. Yeah, okay. So it's going this way. People talk all the time about California just break off into the ocean. And it's gonna take a good long time for that to happen, right? Okay, so where's the strike slip fault in your image here? And how do you know? What have you got? James, do you have one? No, Drew, Drew, Jack, your group?
It's this, it's the big, this thing,
It's
it's red,
It's where?
big, this.
What's that fault called?
Was it the fall call?
Yeah.
Andrea's fault.
That's the San Andreas fault. Okay, how about when we looked a minute ago at those plates, we saw the is there a strike slip fault going on between the Cocos and the Caribbean? No. How about between the Cocos and whatever the blue thing is below it? No. Ooh, the strike slip fault is at which boundary there?
North of
North
Pacific
America.
Plate.
Okay, and what kind of boundary do we call that? Do we know?
Right,
Transform.
Transfer back.
And we have a strike slip fault. That's how we know, because it's going this way, not that way, not this way, but that's your strike slip. Okay. So where might shearing occur?
north.
Okay, Drew, you got, yeah?
Well, we looked it up and there's like a big shear zone
Mm-hmm. Where's that?
and it's not much on the map. But
It's
it
in-
comes into this area and it goes up that way.
Okay.
A lot of the Sierra
Hmm?
Mountain.
And why do you think that is?
Cause I guess cause it's moving up that way, it's gonna cause a
Mhm.
lot of rubbing.
Okay, yeah. How about the terrain there as opposed to the terrain in the southern part of California? What do you think?
There's more mountains up there.
Yeah, there are. There are a lot more mountains up there, right? Okay, so there's a lot more crust there too, right? So what's shearing? Who got a definition for shearing? When you looked it up?
It's just like friction rubbing.
Yes, that's the idea. Yeah, it makes exactly what it sounds like, right? Okay, so let me ask you this about a strike slip fault. What forces are involved there that's causing, so strike slip, it doesn't just it's not always smooth, right? There's at times, what causes that? What causes the more jerky moves when it moves in big chunks? Anybody beside Drew want to guess? Drew?
It's the pressure.
Pressure is part of it.
Like pushing on your hands and trying to move them.
Yes, that's exactly right. If you do this, you get these little jumps.
Just
Why
the
is that?
pressure of your hands
What's there?
pushing together.
Thank you. Friction. Right? There's friction going on there, Mr. Miyagi. Yes, so that's what's going on. You get a lot of friction. All right, so where do most earthquakes in the contiguous, I can't speak today, US occur and why? That's an obvious one now. James? Yeah, California,
Because
right.
there's so much fault.
Because there's this massive strike slip fault there, right? Okay. So we're gonna look at this real quick. So one of the questions said, like, find your most recent earthquakes in California. One of the questions in the lab did. So this is a great little reference here. So this is the Southern California Earthquake Data Center. And you can see here is the whole state of California. And it gives you magnitude based on the size of the little square. And color is time. Was it last hour, last day, last week? So this is not millions or hundreds of years, y'all. This is within a week. Little trembles here and there. So you can see most of them are way down here, 1 or less than 1. Look at this guy.
The big ones are up one.
That's about what? About a 4. Yep. And here's the cool thing. If you tap on this, it'll take you closer and you can see exactly where it was. So look at this. You see these little fault lines here? And it shows you right here, you got Eureka. So Eureka was quite shaky last week, apparently. And then right down here, one of my very best friends from college, she's moving to Florida soon, but she lives right in the middle of all this craziness. She lives in Anaheim. So she's actually she just moved from Anaheim, closer down here. So she's actually like right around, see, here's LA. She's right around in this area. She shakes all the time. And anytime there's like a big one, I call her or text her, make sure she's okay. I don't know how much I'd enjoy that, but this is just part of living here. You can see it's kind of a constant thing. We get these little guys around here sometimes, but they're little guys and they don't happen very often. And people are really like, did that even happen? I don't even remember it. I didn't even feel it. So it does happen here too. So right here, you got USGS. What's USGS? Who knows?
United States
United States geographies.
Not geography,
Geology.
geology, your
Survey.
survey, USGS, US Geological Survey. So this is a kind of a, I wish I could get a clearer one, but this is the best one I could find. It's a little blurry. But so they take, for example, this is Uniform California Earthquake Rupture Forecast. So this is kind of like what you guys were doing. So they're forecasting where earthquakes will occur and how often. So it says, because it's a little blurry, I'll read it for you. I'll read down here first. It says,
They're more accurate than us.
oh, yeah, possibly. So it says faults are shown by the rectangles outlined in black. You can see them here, right? The entire colored area represents Greater California, and the white lines across the middle defines Northern versus Southern California. Results do not include earthquakes on the Cascadia subduction zone, a 750-mile offshore fault that extends about 150 miles into California from Oregon and Washington to the north. That was, remember last week we looked at Cascade Mountains and volcanoes? So that's way up here. So it's not including that data. So it says here, three-dimensional perspective view, sort of three-dimensional, as three-dimensional as two-dimensional can be, of the likelihood of each region of California will experience a magnitude 6.7 or larger earthquake in the next 30 years. 6.7 matches the magnitude of the 1994 Northridge earthquake, and 30 years is the typical duration of a homeowner mortgage. So think about it here. What's this information for? Who's going to use this? What's the purpose of this? Ah, there we go again. We're back to insurance companies. All right. So your typical homeowner mortgage is 30 years. Now, I'm very, very curious if that is an average for the state. I doubt it is. Does anybody know what the typical for this area, how long families typically stay, like the average? I think it's the average actually, for people to live within Forsyth County before moving home. It doesn't mean you have to leave the county, you just shift houses. 5 years. This is a really transient area. Why is this area so transient like that? Why do you think? Use it.
Because new areas are forming with better houses.
That's part of it. Constantly building new neighborhoods. That's a big part of it. Why else? What do we do here? Is there like a big industry that everybody in Forsyth and Gwinnett goes and works for? Like one big factory where everybody works? No, we're not that kind of town. There are towns like that, right? Where there's like one coal mine or one manufacturing plant and everybody works there, so nobody ever moves. So think about, why would people here move so much?
Earthquakes?
No, here, I'm talking here, where we are now.
Jobs.
Jobs, there we go. Okay, what kind of jobs primarily do we have around this area? Do you know? Like compared to other parts of the country? What do you think? Yeah, we do a lot of high tech basically. So we have a lot of tech jobs here, a lot of engineering jobs, high tech jobs. We are within travel distance to the busiest airport in the country. So this is a place for a lot of people who have business jobs related to technology. And a lot of those people move frequently because the job shift. How many of you have parents that are involved in technology for their job? Oh, well, look at this. What do you know? Shocker, right? All right. Now, if I asked you that in Oklahoma, do you think you'd all raise your hand? No, I mean, that's the point. Yeah. How many of you have parents who farm, like the whole rim, right? So this 30 years, I'm thinking, is an average of the whole state, because I guarantee you, San Francisco and California do not have 30-year mortgages as their average. Those are big cities. People are moving in, moving out. They probably have more rentals in these areas than out here. Out here, if you're living out here, you're growing grapes and stuff and making wine all day, you're not going anywhere for 30 years. So they take this 30-year average and then they put, here's your percentage likelihood in 30 years. So if you live over here, it's like 1 in 1,000% likelihood that you're going to deal with a 6.7 during the course of your 30-year mortgage. Whereas if you live along the fault here, yikes, right? And that absolutely does impact insurance. All right, so would you build your dream house here? Somewhere along the fault? Near it? Anywhere near it? based on the information that you came up with today.
If you want to take
Depends
a
on the
risk.
dream house.
All right, where it depends on your dream house. I found this is the gaudiest mansion I could find. I tried to do the Barbie dream house, but it just doesn't look as cool as it used to. So
If it's a trampoline, you could.
if it's, okay, that's good. All right, so somebody show me your, actually, everybody hold up your 50-year maps. Let's see what we get. All right. All right, now look, compare them to each other. Do we see much difference? Did much happen over 50 years? Not a whole lot, right? Everybody's looks about the same, I think.
Fairly, but it's really impossible to.
Yeah, you really can't, you almost couldn't see it. So how did you get, somebody explain to me how you got that 50-year measurement. What'd you do, James?
Looked up how fast
Mhm. The fault moves?
Was moved.
Yeah, what'd you find?
it said between 30 and 50 millimeters a year.
Wow,
So
okay.
Took the median
Mhm.
and multiplied it by the amount of years.
That's a good one. So on the ruler here, 40, you're doing 40 millimeters. Sorry, let me get the clear one, probably easier to see. So 40 millimeters is how many centimeters? Okay, so we're talking, such as your average in a year, right? And of course, it depends on where you are along that fault because, you know, some places along that fault are going to move more than others. And then there's going to be the strike slip issue. Now, if we put a house on the fault and this much movement occurred in a year, would it affect the house?
A little bit.
Oh, yeah, probably a lot more than you would expect. It would probably have foundation issues and everything else. But if you look at it, when you back up and look at it from the whole state, it doesn't look like much. All right, how about your 100-year maps? Who's got those? Let's see. Okay, can see a little more shift. Okay, there we go. Everybody's looks about the same, right? A little bit more shift. So basically what'd you do there? You took the answer you had before and what? You doubled it, right? Okay, good deal. And how about your 1,000-year? Multiplied it by 10. How do we see it now? Okay, little more. Yeah, you spread yours out a lot. There you go. No, that's okay. I see. There you go. All right. So in 1,000 years, how far did it move? What's the average? Who found it?
131.2 feet.
131.2 feet.
We got 167.
167 feet. What'd y'all get? Do you know? 166. What'd you get? So somewhere around 150 feet, probably. It would be a great, and we could go with that. So 150 feet in 1,000 years. Somebody tell me what's 150 feet? Give me something that is 150 feet that you see. That's a good one. Half a football field. Okay, that's a lot. 1,000 years is a long time, but that's a lot. So, hang on, Lily's joining in. Hi, Lily. We were just kind of going over lab. We're about to start class. All right. So then lastly, here's a good little graphic here. And I think this one was, this was not USGS, but New York Times. So this shows the Gulf, California here widening. So this is in 50 million years. You can see California is now kind of up here by Washington, and much of this doesn't look like, look at the mountains in the middle here. See how they change? Right? Okay. And then it's 250 million years. Oh, there it goes. Bye-bye. So this was, I'm sorry, this was 25 million. This one's 50 million, and this one's 250 million. So will California float off into the ocean?
No.
Yeah, well, much.
California been an island.
Yeah, but are we gonna live to see it?
I mean,
No,
no.
we're not. All right, find yourself ready for class. Do whatever you need to do.
Cryostasis, a little time travel.
I'm not doing that, man. When I die, I want to just die. Let's see. All right, gathering up. Okay, and I got stuff to hand out. If you want me to make copies of your team's lab, just put them up there in the folder and be sure to put your team's name on them, staple them together, and I'll happily stick them all on one page for you so you can see. Otherwise, y'all can do whatever you want with it. Okay, handing out things. Drew and Drew, Bailey.
I heard Dare trying to say, she tried to take myself.
All right.
there. I was not. once that. Wrong one. That is.
Well, we can take now to work on the floor. Okay.
Where did I leave? What? I'm like, I had a
Here, you
pencil.
wanna take your- Yeah.
Wow.
No, sorry, I'm gonna get that.
Jack, so you
This
don't
one.
like our dates?
Yeah, what one here?
Yes.
All right.
No, oh, no.
This is Lazy Chaos. Okay, this is Caitlin.
Okay.
You. James, this is also you. Young is here, you. Parker. Go, Jack, my friend. So I got. I have you, so. This is your team, so you can share that with Drew and the rest of your team, I think. No, I got you here, you're. I'm supposed to love you. Okay. And Milo. Chloe. My logo. Oh, he's over there. Chloe. You got those? We can get you other than you done. You got those?
Graders with a
Alright,
Z,
Jack.
because we're cool, we put a Z.
Jack, this is you.
That's me.
You.
That's me.
My logo, this is. Where did you go? You go. My logo, this is you.
What'd you get?
All right.
On the-
And this is Lily, Drew, and Drew.
That's
Drew.
800.
All right, so.
What's the 86?
So, I think Bailey had pointed out that the score looked weird in teacher ease. I'm gonna make sure I fix it. If you want to know what your lab score is out of 100, just double it, right? Because it was a 50-point lab. I think the auto setting for lab is 100 points, so I have to go in and change it. You got what? Okay, there you go. So not terrible. All righty, so we're talking earthquakes today. Did y'all please tell me here, this must start. Oh, this design is called It's Not My Fault. Isn't that amazing? I love nerdy things, you know me. Okay, so earthquakes. So we're going to talk about forces within the earth first, and we can all do these with our hands because it really does help you understand what is happening here. So we're going to talk first about stress and strain. Who can explain stress? Drew.
Stress is push, strain is strain.
Okay, so stress is a push. So see that first picture there at the top with the hands, this, like you're praying, that's a stress. You can remember that by saying when you're stressed, you can pray, right? That helps you remember what's what between stress and strain. So stress is your total force acting on crustal rocks per unit of area. How about strain, Yusuf? Okay, we're pulling apart there. So here's your second one here. So strain is the deform of materials as a result of the stress. And then you have elastic deformation. Can anybody explain what that is? That's a fun one. Drew?
Last information
Mm-hmm.
is how much stress and strain you put on an object before it becomes, before it changes. It's like
Okay.
a pencil.
Mm-hmm. Like how much can,
Bends it a little bit,
right?
but then it's too, I'm not gonna break it. If you bend it too hard, it's gonna.
Okay, that's great. So elastic deformation, low stress material is compressed, bent, or stressed. Did you know that from somewhere else, or did you just see it in this chapter? Okay, how'd you know it?
You guys should look up Jay Laser on YouTube. Real life.
Yeah?
He makes up like real life Avengers gadgets, and he made a working Captain America shield that actually bounced off of things.
Oh, I've seen that.
Yeah, and he was
I didn't watch it.
and he made fiberglass ring.
Okay.
Talking about that.
There you go. So elastic deformation, you want some amount of elasticity for your building material if you're building anywhere. You don't want brittle for sure. You ever watch the trees in the wind and see them blow around? I think I talked last year about the trees that are now like the scourge of southern suburbia. They're those Bradford pear trees. You've all seen them. They stink sometimes. Yeah, they have little white flowers. They're beautiful. They smell. Yeah. Mm-hmm.
My neighbor has like a big.
You have what?
We have tons of them.
Tons of them? Yep.
One like right across the sheet.
Yep. Well, they
It's like-
happen to be more brittle than a lot of other trees. And that's why they, at this point, are starting to snap. Over the last 10 years, they're just starting to break and fall apart. And that's because when the South suddenly began filling up with suburbs, which happened much, shh, y'all back there, which happened much later than it did up in the North, where you got a lot of more industrial cities. When the South started filling up, they're like, oh, we have to put something pretty in. So they put in all these Bradford pears. And now they're all reaching the age where that's kind of as far as they can go without snapping off. So that's where they're headed. All right, so what's plastic deformation? If elastic is how much something can bend before it breaks, what's plastic? What do you think, Caitlin?
It won't go back.
It won't go back. Right, okay, so this is when you've stressed it beyond its elastic limit. So it's gonna cause permanent deformation of your material, okay? And it doesn't return to its previous state, which is what Caitlin was saying. And when the stress is removed. So it's elastic deformation when you put stress on it. And then it's ductile deformation when you pull the stress off of it. But if it doesn't go back to its original state, then we can say that we've had some plastic deformation. And if you look here, there's a little graph and it's got stress going this way and strain going that way. And you can see ductile material and brittle material. What's ductile mean? You know, or are you going to say something different? Oh, what were you going to say?
It's like a rubber band when you break your rubber band.
Mhm.
Plastic.
That's right. That's right. Very good. So ductile means it's kind of bendable, similar to malleable. If you remember, we talked about way back in chemistry, we talked about what was malleable, like certain metals are malleable, like copper is very malleable. You can do a lot of bending. But the thing is with malleable, it tends to be a lot of plastic deformation. They'll bend, but they don't necessarily bounce back. So ductile materials kind of bend and bounce back, but look at the brittle material, snap, like just doesn't do it, right? So within the forces within the earth, we have faults. We got different kinds of faults right here. So any fracture or system of fractures along which earth moves are what we call a fault. So we have a type of fault that has compression and it causes horizontal and vertical movement. So horizontal and vertical. So that's kind of like this deal. So what kind of fault is that? Yusuf.
Reverse fault.
Okay, reverse fault. Anybody agree? He's got it. All right, so then we have this fault where you've got tension that causes horizontal and vertical movement, not compression, but tension, Liam.
Normal.
All right, normal. And then we have the ones that cause shear, and that was lab, Piper. Strike slip. All right, so let's have a look at the pictures. You got your normal fault. You got it's moving apart here. You've got compression, and that there's compression here because this is being I'm sorry, there's tension because it's being pulled, right? These are being pulled away, and you've got tension where the pulling is happening. And then you've got normal faults. Reverse faults. I'm sorry, I read that backwards. These pictures are opposite words. So you've got reverse faults here, and that's where you've got your compression and then your strike slip. Now they got different types of strike slips. We're not going to get picky about what kind of strike slip is what kind of strike slip. Just know that they exist.
It's like the first, the right.
So if you see here, this is great. Somebody built, I don't even remember where this is, where I got this picture, but somebody built this great little, I don't know, what would you call that? Like a
Puzzles.
kind of, yeah, it's monitoring how those faults are moving. So if it would have been better if they'd have like put numbers on them, like 1, 1, 2, 2, so you could see which way things were going, or A, B, B, but still, you can see that it definitely has shifted from where they started. So we have our types of faults. So this video is just going to kind of review what we just said about one. Yeah, it should clear up here. Go away.
Welcome to the Nevada Science. I was there. The Earth is a dynamic and constant movement. The tectonic plates which sit on the ascenosphere shift and move. This movement creates stress, and the rocks at the surface may break in response to this.
He looks like that.
When the rock breaks, cracks are created, which are called faults. On either side of the fault are blocks of rock called fault blocks. When these fault blocks move, earthquakes may occur. There are 3 main types of faults: strike slip faults, normal faults, and reverse faults. Let's first determine the difference between the hanging wall and the foot wall. In all faults except for vertical faults, the hanging wall is the block above the fault and the foot wall is below. Two simple ways to identify the foot and hanging walls: to place your finger on the fault surface and move it up. It will automatically be located on the hanging wall. The hanging wall will have an angle less than 90 degrees at the top, and the foot wall will have an angle greater than 90 degrees at the top. Let's get started with the fault. In a strike slip fault, the blocks move past each other horizontally. A strike slip fault occurs due to shear stress, which pushes the rocks horizontally but in opposite directions. Strike slip faults are common along transform boundaries like the San Andreas fault. During a normal fault, the hanging wall moves down relative to the foot wall. These faults are called normal because this is what you would normally expect the faults to do. Normal faults are a result of tension, which stresses or pulls the rock apart. Normal faults are common along divergent boundaries. The Basin Range area is an example of this. A reverse fault occurs when the hanging wall moves up the foot wall. These are called reverse because this is the reverse of what you expect as a result of gravity. Reverse faults occur as a result of compression, which is stress that squeezes the rocks together. The San Gabriel Mountains are caused by reverse faults. I hope this video helps with faults. Thanks for watching.
We hope so too.
And Moo Math uploads
Thanks, Momo.
new math or something.
Remember.
every day. Please
So I do want you guys to know hanging wall and foot wall, as well as these three types of faults. Okay, for this unit, these are things that I'm going to want you to remember. I should have put my little Rico symbol up there. I keep forgetting to do that. All right, so seismic waves. So this is your vibration of the ground produced during an earthquake. And we have three different types of what they call body waves. Funny enough, in the 80s, body waves is what every girl wanted to have permed into her hair. It was called a body wave, just big 80s hair. So we have different types of waves. We clearly have P wave, S wave, and surface wave. So what does P wave stand for? Piper. Primary waves. So what happens here is these squeeze and push the rocks in a direction that the wave is going. So that is this kind of movement, right? You're squeezing and pushing in the direction that the wave is going. So it's like if you took a slinky, I should have brought my slinky down, and you and your friends stood there, one of you pushed, and it made that little wave that goes through like this. That's what we're talking about. Okay, what's an S wave, Jack?
Secondary.
Okay, secondary waves. Now, these are the ones that you feel. It says S waves, second set of waves to be felt. Sorry, move the rocks at right angles in relation to the direction of the wave. So what does that mean? Right angles in relation to the direction of the wave. So if the wave's going this way, boom, boom, boom. Right angles would be which way? Yeah, okay. And then last was Liam.
Surface waves.
Surface waves. Okay, now these are the ones that really get you, right? So surface waves are the third set to be felt. They're slow. They move along the surface. They just kind of right along the surface. So this right here would be a reading of how the waves come in. You get the little ones, then you get these guys, and then these surface waves go on for a while, right? So here we've got some graphics. Let's take a look. Here's the slinky thing I was just talking about. So here's your slinky at rest, just sitting there stretched out between you and a little eye hook on the wall. If you push the slinky, that's compression, and that is your wave direction, okay? So this kind of shows how P waves work. And then you also have to think there's matter and particles, and the particles are moving kind of both ways. Think about how that would look, right? So this shows right here, back and forth motion produced as P waves travel. So you can see there's compression, tension, compression, sort of all the way down the line, right? Okay, then you can see S waves with a rope. If you shake the rope this way or this way, either of which are right angles to a compression wave. Does that make sense? Right angles to the wave. Does everybody understand what I mean by that? Your wave's going this way, boom, boom, boom. And you go this way or this way, that's at right angles. Lily can't see what I'm doing. I'm sorry, Lily. So if you have, where's my hand? Your wave goes this way, touch it. That's your P wave, but your S wave is gonna go either this way or this way. Okay. And Alex will be looking at that, thinking I'm crazy too. Okay. So here's how your S waves look. You can see them up and down, up and down, up and down. And so this stuff is really like shaking and cracking, and this stuff is really, this is a lot of bending, right? So then you only have your one type of surface wave, this one says, moves the ground from side to side and can damage foundations of buildings. This looks fun, doesn't it? And another type travels along the surface, much like rolling ocean waves. And the arrows show the movement of rocks as the wave passes. Motion follows the shape of an ellipse. What's an ellipse? Yeah, like an oval. So basically you've got, what you've got here is you've got these guys that can either go, you can think of this as sort of like horizontally versus vertically, right? Kind of, sort of in relation to the ground. So what is the focus of an earthquake? Who can tell me what the focus is? Yusuf. Point where, okay, so it's the point at which the waves originate, and it's usually several kilometers below the surface. So this is not near the surface, and it doesn't describe like geographically where something took place in relation to a map. It tells you where it happened way down deep in the rocks. So right here, for example, this is where the shifting occurs. Now, obviously you got a whole block here, right? You got, which one? Okay, what words are written on the hanging wall versus the foot wall? Who can tell me? Let's make sure we can identify them. Which one's the hanging wall? What's it say on it? There's words on it.
Oh,
Just for the sake of the diagram.
oh, yes, oh.
So we have, okay, let's put it this way. This says wave fronts, this says focus. Is wave fronts written here on the hanging wall or the foot wall?
Football. Football.
Okay, and then this one is written on the, and how do you know? What did it say to do? Put your finger on the fault and go up, and you're automatically on the hanging wall, right? Okay, so although the whole thing can shift, there's going to be a spot where most of the shifting takes place, because you have to remember, it's not one, like Earth's interior is not this like perfectly uniform solid block, right? It's made of, yeah, it's got areas that are softer, areas that are more brittle, areas under more tension, areas under less tension. So this would be where it actually originates. Okay, what were you going to say? Or you answer the next one? Oh, what? Oh, you're scratching your hair? Okay. You're asking me a question. Okay, epicenter. What's epicenter? All right, now you go, Piper.
Point above the socket.
There you go.
Point above the focus on the top.
That's it. Okay, so your focus is where it's happening, but your epicenter is on the surface, right? So if you go straight up, straight up from where you've got your focus, then you have your epicenter. Yes, it is. Do you want to be at the epicenter of an earthquake?
Oh.
How about in the eye of a hurricane?
Yeah.
Yes. Oh, very good. You guys remember. Good. Why do you want to be in the eye of a hurricane?
Because it's calm.
Nothing's going on in there.
Better keep.
Do you want to be in the eye wall?
Good.
No. Okay, good. All right. Excellent.
Yeah.
Yeah. Could be very windy and wet. All right. So, oh yes, that McLaren. That was the worst. Oh my goodness. It was, that's like, I'm sorry. I like cars. I like cars. So that makes me very sad when that little McLaren floated away. All right. So how do we detect and measure earthquakes? So what were you going to say? Kitten, go ahead. Tell me. Okay. Yeah. Seismometer is what we use to detect the earthquake. So here right here, what have we got? Meter. Okay. What's this mean? This is another one of those good old Latin Greek roots. What do you think meter is? I mean, we know what a meter is. We use it. What do you think, Drew? It's a measurement. Okay. Measurement is meter. And then seismo, this has to do with what? Use it. Yeah, just movement. Like this is, we're getting movement within the earth. So a seismometer, because we're going to do seismometer. It's another one of those ones like thermometer, seismometer. This is going to measure vibrations. So it's the measuring. All right. Are you going to tell me, Bailey, what do we record it with? Seismogram. Okay. So it's been recorded here, and this is the record that's produced. Now, how do we know the difference between the two? How you gonna do it? Go, Billy. There you go, gram. Yes, this is one of those kind of weird ones. All right. We measure with grams too, don't we? So we've got like, we measure with this and we measure with that. Gram is kind of one of the weird ones here. Usually you would see graph. You know what I mean? Like when you do an EKG, that's an electrocardiogram. Sometimes we see gram where you would think you would see graph, right? Because graph means like to write or to, you know, to produce a record of. But in this case, it's going to be gram. So if you can remember that graph and gram are sometimes used where you would expect one or the other to be, that G-R-A should be enough to help you keep seismometer and seismogram separate in your head, okay? So what do I want here? Some kind of curve, consolidated data, which provides the average travel times of P and S waves whenever they occur on Earth. What's this one, Drew?
That's a seismogram?
If we did seismometer and seismogram, and we're looking for some kind of curve. Do you know where it is?
Right,
A what? Frame?
or the.
What you think?
A travel time curve.
Yusuf's excited. Yeah, travel time curve is what we're looking for. All right, travel time curve. So if you had a travel time curve, first off, you're producing a curve. So what does that tell you about how you're plotting something? What are we doing? Right, but we're gonna, if we're making a graph and we're producing a curve, what do we have to have on that graph to get the points to produce the curve? Ah, good job. X and Y axis. All right. Bailey is with it today. You have to have an X and a Y axis. Which one is X? Horizontal or vertical? X goes this way and Y goes this way. How can you remember that Y goes this way? Yeah, there's a little line under it. Piper's got, she just remembers it. So if you look at the letter Y, right, it's like this, and you got this line that comes down. If you would just continue drawing that line down, you know that your vertical axis is going to be your Y, and then your X is going to be your horizontal axis. So if it says travel time curve, what do you think you might see on those axes? What do you think? Yusuf, what do you think?
A curve.
Okay, they're going to produce a curve. Well, what are you got axes, how are they going to be labeled? What do you think? Yeah, or the other way around. So one of them is going to say time, and the other is going to say travel, or time and travel, whichever way you want to do it, right? So you're going to have an X and Y axis, and you're going to plot out your, how far did it go? So one of them will be distance, and one of them will be time. And when you put distance and time together on the map and you plot it out, you're going to make a curve, and this is your curve. All right, so what is the distance from the epicenter? Somebody explain to me what that means. What do you think it would mean? How would you describe distance from the epicenter? Kind of self-described. How are they going to measure it? What do you think? There you go. Okay, so we're going to use this data in this curve. James? Could be. I don't know. Why? What are you noticing about it?
The lines are going like that, which is the fast screen.
Very good. I know that is really crazy that this diagram, somebody got it. So this diagram, yeah, it's kind of weird, right? Like, how is this? I think the point is you got a string here. I mean, a spring here, because I looked at it too and I was like, So you have a spring here and this is a weight. So the weight's going to bounce up and down. And as it bounces up and down, you're going to get this. But I had to look at it for a minute too. Does it make sense now? If you can see the spring is like, there it is. So that would work like this thing's going bounce, 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 bounce as the earth shakes, and this thing's going to spin. So it's going to spit out this lovely little pattern force. So yes, so your distance from your epicenter is the farther apart the waves on a seismogram, the more distant from the epicenter, which is basically what we're all saying here, right? All right, so here's how we triangulate. Where else do we triangulate or use similar types of, similar process? Do you guys remember, what were you gonna say? To find people, right? Do you guys remember when we did way back in like the very first chapter, very first lesson, we talked about or second lesson, I think we talked about maps, and we talked about how you got satellite technology now, and you actually, 4 is what they use, right? But you can use 3 points. Satellites are a little different because you're not on the same plane, but you can use 3 points to determine where something is located. So this is how it works in case anybody wasn't 100% clear. So it's good to share because it's a good
Look at
video.
how to locate
Whoa, hello, I bumped it. Now it's mad at me. Sorry.
the epicenter using triangulation.
Oh, that's fun.
method.
Don't do that. Don't do that. Hang on, sorry. Give it a second. It's being silly. Where did it go? Right here. All right, try it again. Maybe not.
So here is a map. of the
Oh, this
world.
is great.
And
It's not a map.
if you
Don't
zoom in
lie.
on a particular region, we'll look at North.
Isn't it? Best map ever.
Now that.
Okay, let's try going forward again. Okay, this looks more promising. Sorry, gang.
Look at how to locate the epicenter of an earthquake using triangulation. All right, so here is a map of the world, and we're going to zoom in on a particular region. We'll look at North America.
Shocker.
And
Right
let's
there.
imagine that there was an earthquake somewhere in North America. Well, the question arises, where was the epicenter of that earthquake? Now, we may be able to get a general idea of where the epicenter was based on looking at the severity of damage, eyewitness reports, etc. But if you want to pinpoint the actual location of the epicenter,
And I'm gonna pause it for just a second, let him buffer a bit. Maybe that's why he's chopped up. All right,
and so let's look at how we're going to do that. First off, in order to pinpoint the epicenter, you need a minimum of 3 seismic stations. So let's pop a few of these seismic stations on the map. Let's say we have one here in California, one over in Canada, and one down south here, labeled 1, 2, and 3. Now, these are the locations where we have seismometers actively monitoring the shaking the Earth's crust. Of course, we have seismic all over the world. In order to use this triangulation method, we need at least 3 of these or data.
come on, load a little more. I hate it when it works fine before you get here. And then it's like taking a car to the mechanic, y'all. All right,
From 3 of them.
there you go.
So step 1 is going to be to take the data, the seismograms from each of the stations and determine each of their epicenter distances. That is to say, I want to know how far point 1 is from the earthquake, how far point 2 is from the earthquake, and how far point 3 is from the earthquake. And this is just fairly easily accomplished. You would simply find out the difference in arrival times for the P waves and S waves, and then use a travel time graph to calculate the distances. So let's say you have done that and you have established that seismic station 1 is approximately 700 kilometers from the earthquake. So something like this. But the problem is, we don't know if it's 700 kilometers in this direction, in this direction, in this direction. We don't know. It could be 700 kilometers in any direction. So what we can do is draw a circle around point 1 with a radius of 700 kilometers. And now we know that the epicenter is somewhere on that circle, somewhere on that line. But again, that's not good enough because we want to pinpoint the location. So let's turn our attention to the location 2. And say we did our math and we found that location 2 is 3,000 kilometers from the epicenter. Now, again, it could be 3,000 kilometers in any direction. So we will draw a circle around point 2 with a radius of 3,000 kilometers. Now, notice something. If you do this properly, your circle should intersect.
Stop. No, I hate it. Sorry.
Most likely in 2 places. What that means is that it can happen either here at this intersection or here at this intersection. But again, that's not good enough because we want to know exactly where that
Okay.
center was. So leads us to station 3. We take our diagram, we do our math, and we determine that station 3 is approximately 3,500 kilometers from the epicenter. So again, it could be in any direction. So we take the drawing compass and we draw our circle with radius 3,500 kilometers. Now, if this works out properly, all 3 circles should intersect in one
that.
single point.
California, who could have guessed that?
Why does it do that? Stupid. Obviously, it's the one up in the north, right?
One point is your
There you go.
epicenter, shown by the pink star. This is what we call the triangulation method for locating the earthquake epicenter.
So I do want you to know how to do that. You might just have a homework question that includes some of that kind of information. Does everybody have a compass at home? Anybody have a compass? You got a compass?
Yeah, I will.
Compass is helpful. If you don't have a compass, yeah, if you don't have I'm talking not a north, south, east, west compass. I'm talking about like a yeah.
Oh, yeah.
You do this. So if you don't have a compass, another way to do it is to use 2 pencils and a string. Measure with your string, tie it around the 2 pencils, hold one still, take the other, make your circle, okay? And you would make your distance the same as you're gonna have a key, right? Of some kind on a map that'll tell you distance. Uh-huh.
I use the same method for like copying triangles.
Oh, okay, yes. Uh-huh. All right. So somebody tell me about, so here's seismic waves, basically. They can tell us information about Earth's interior, right? We've got clues now because we can't see it. We've got to use data. Remember it talked about Newton, was it last lesson or the one before, where it talked about how Newton knew that that Earth couldn't be solid all the way through because of the way that stuff like this, you know, the way earthquakes and things perform. So let's think about internal structure. What kind of clues do seismograms give us with regard to Earth's internal structure? What have you got? Anybody got? It should be kind of right there in your notes, I think. All right, Yusuf, what do you have?
Like size, like when the waves come out,
Mhm.
seismograph will hold the lines.
Mhm.
And if it's in the area that has like denser material,
Mm,
we'll go a little bit because denser material absorbs the waves a little bit.
there you go. Okay, very good. This is exactly what we're getting at. So it will give us some information about the composition and the internal structure of Earth. So first, let's watch this. Keep that in mind.
Planet Earth. If you look closer, you'll see that a whole other world exists beneath the surface of land and sea. Layer after layer of rock structures go deep into the Earth's crust, mile after mile. And trapped within these structures, along with other liquids and solids, you'll often find deposits of oil and natural gas, the world's 2 most important sources of energy. These famous fuel pools are in constant demand because they make the world go round day in and day out. So how do you find something that's completely hidden beneath the Earth's surface? It's a mystery that people in the oil and gas industry are always trying to solve, and for very good reason. Drilling for hydrocarbons is expensive. And before they spend money on equipment and crews, exploration and production companies need a reliable strategy for pinpointing where to drill. Geoscientists have a secret weapon called seismic exploration,
Secret weapon.
and it involves sending acoustic energy, which takes the form of wavelets, into the ground to get a sound picture beneath the surface. It's complicated, so let's start with the analogy of bats. Bats can't see very well, so they send out little waves of sound that bounce off of objects and then go back to their ears. It's called sonar. It gives them what you might call a sound picture of their world. That's a good example of how nature already uses a form of seismic acoustic imaging to locate objects. Doctors also use it for ultrasound imaging. Geoscientists use man-made tools to make the sound wavelets, listen to them, and then record them. When you want to know if oil and gas deposits are in a particular area, geophysical companies bring large trucks that have big vibrators on them. Most of the time, this is what generates the acoustic energy or vibration. They use geophones or very sensitive seismic microphones to hear the reflected sound. But sometimes they set off small buried charges. They set many geophones on the ground in a line, and they are attached to a recorder inside another truck. The vibrators send thousands of waves down into all the different layers of the earth. Some of the wavelets bounce off of the boundary between the rocks below the surface and are reflected back to the geophones that are waiting to record them. Each geophone along the cable sends the received wavelets to the recording truck where they're recorded and stored. How do the wavelets reach into the subsurface of the ocean? That's offshore seismic, and it just requires a different device to send out the wavelets and record those that are reflected back. Out at sea, a seismic crew worked off a vessel with a specially designed back end, so it's easier to lay floating cables or streamers. And all along the length of the streamers, microphones called hydrophones are attached one after another. Several of these hydrophone streamers are put behind the vessel at once. Acoustic sources are towed behind the vessel in front of the streamers and release compressed air, which creates the wavelets. These wavelets travel the water and into the subsurface below, where, just like on land, they bounce off the rock layers and then return to the hydrophones to be recorded. Here's what it's like after it's been recorded. Basically, it's a bunch of squiggles. There are still a few more steps to go before it begins to look like an actual picture of the Earth's interior. Right now, the data is still in its raw form. To get a picture that actually looks like the Earth beneath us, the data has to be processed. It takes a large supercomputing PC cluster to process the seismic data.
Woohoo.
These computers go through all the different traces made by the wavelets and filter out everything we don't need, such as vibrations made by a tractor in a field nearby. Using really amazing computer applications and working on state-of-the-art workstations, geoscientists can see the seismic data translated into a 3D picture. You might be thinking, I don't see any oil and gas there. But believe it or not, geoscientists can look at this processed data with their trained eyes and make an informed decision about whether or not oil and gas deposits are in the geologic structures. Seismic data leads to a high percentage of real depth with less risk to the environment. And in a world where the demand for oil and gas is increasing faster than the supply, good seismic information will lead to more affordable energy.
So if an earthquake sends seismic waves, it can give information too. But what is important would be, if you're a geoscientist, you have to kind of know what to expect. If you know the internal structure of the Earth in a particular area, then that's going to help you interpret what the seismic waves mean, right? Because say you're in an area where you've got lots of fluid, and there's another area where it's very, very dense rock. Those waves are going to come at a different rate, right? So this information here that can help you get all kinds of data for drilling and whatnot is also information that can help explain exactly where the epicenter of an earthquake is, or why it was felt over here but not over there. And it has to do with the composition of the Earth's interior. So you got, come on, go away, not you. Go away. Go away. There we go. So Earth's internal structure, temperature, density, and the type of material affect the direction and speed of the waves. And S waves don't go through. Ah! S waves don't go through liquid. Stop it. What are you?
One more line free.
How many times have I hit pause here?
No nonsense, just business.
If you look closer, you'll see that a whole new world
You're
is
crazy.
the surface of land and sea.
Just ignore that for a minute. So your S waves don't go through liquid. So if you're looking for oil or an aquifer, that's a good way to find one, right? And then where Earth's composition is concerned, knowledge of this kind of the behavior of these waves contributes to your whole understanding of where everything is. And then you can use imaging like they showed in this video. I think this imaging is particularly interesting. Like I'm not one who's like, woo, geology is my favorite science discipline, because it's really not. But I think that kind of imaging stuff is really, really interesting. I mean, somebody has to do all the computer programming that's essential for that, and then somebody else has to do the interpreting. And there's been similar stuff recently that they've used for space. Who remembers the black hole picture from like 2 years ago? Remember that? Yeah. Okay. So that's the same thing. So that's the same kind of thing. It was data that was converted to help produce an image. Like you're not getting it's not a photograph, right? You can't take a photograph of things you can't see, but you can get non-visual data and then use computer programming to convert it to visual data, which is really pretty cool when you think about it. So obviously that takes a lot of trial and error to figure out what works, what doesn't work. But if you ever see the pictures of the oil rigs out in the middle of the ocean and you're like, how the heck did they know there was oil under there? It's not like it's spurting up like in, you know, the Beverly Hillbillies opening scenes, you know? Do you guys know the Beverly Hillbillies? Anybody know that one? It's a TV show from, I think, the 50s and 60s. Family lived in Texas and they're real hillbillies. Like that's the joke. They're rubes, right? They're like Southern idiots, kind of is the idea, right? But they're in Texas, actually, I think is where they are. And they've got oil coming up on their land. So they sell their land, they make a ton of money, and then they move to sophisticated Beverly Hills where they continue to be ridiculous, which is the whole point of the TV show. But yeah, sometimes crude oil will come right up through the surface, right? On the land, and you can see it. And you're like, holy moly, there's oil here because pressure's pushing it up. But if you see those big oil rigs out in the middle of the ocean somewhere or images of them, that's how that happens. Because they can sense with their different technology can pick up what's beneath the surface.
Then if it send sound inside the water,
Mhm.
then the water might like kind of make the waves go away.
Yeah, so your S waves aren't gonna go through water, but the type of wave they're using for sonar will. So it's a different type of wave. And it's interesting because you have to think about it. It has to be able to go through the water, but still tell you if there's liquid underneath. So it can't just go all the way through. So they refer to them as wavelets. When you, yeah, compress. So that's this kind of a thing, right? It's your straight kind of. So when you say wavelet, what does that make you think? What is, when you put let at the end of something, what's it mean?
Like little.
Yeah, like the little thing. Yeah, what's another word that has that? Can you think of another word for somebody's? Piglet, that's a great one. Piglet is a great one. Okay, yeah.
Like chiclet.
Chiclet. Okay, there you go. That's gum. But yeah, you get the idea. So they're tiny waves. That's what they're sending. They're not sending big old massive compression waves that would seriously bother all the critters. That's why they say don't tap on fish tanks. You're creating compression waves, right? That's not, they don't like that. I wouldn't like that. Right. All right. So nope. Go. Right. Did that not do? I did that. Now it needs to go to the next one. Okay. So we have 3 different, how do we call these? Descriptors for how an earthquake affects the land. We have magnitude, amplitude, and intensity. This isn't just for earthquakes. These are for waves in general. So next year when we do physical science, we're going to talk about amplitude and we're going to talk about wavelength and things like that. So this sort of thought about waves and wave behavior and wave theory is exactly the type of stuff we'll be talking about next year. Actually, I want to do, if I can figure out a way to do it, I'm going to try and alter my physical science labs a little bit because I want to do one of the wave pendulum experiments. If you've not seen them, it's really cool. You take like a billiard ball is a great example, and you attach them to cables that are not ductile. They're not going to stretch, bend, and you make them so they are all just a little longer than the next. And then if you push them and let them go at the same time, the waves will make different patterns. It's very mathematical, actually. But the waves will make different patterns, and you'll see points where the balls like all cross each other like this. And then you'll see points where they do this. And then you'll see points where it's like, bip, 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 and then they'll come back together and then they'll split up again. And it's really, really, really neat. And I'd like to make like a big one. I think that would be cool to have and just be able to show. Yeah, no, I don't want to do it inside. I might do it down under the deck or something, but I think it would be cool to have. They're really, really neat. So keep in mind that kind of stuff when you're thinking about this wave stuff. Don't just throw it out of your head and go, earthquakes are done. I don't have to remember about waves because they will come back next year. So magnitude, what's magnitude? All right, Caitlin.
The amount of energy released by an earthquake.
There you go. So magnitude has to do with your energy of the largest waves. We're going to consider the largest waves when we're talking about the energy. So what's the amplitude?
The height of the wave.
There you go. That's a good way to put it. Your height of the wave. All right. For my 2 gymnasts in the room, there's a team named Amplitude.
I was about to say, I've heard that before.
Doesn't that make sense? If you're, it's a great name actually for a team. Height, bounce, going up. All right. So intensity, what's this one? All right, Liam.
The amount of damage earthquake
There you go.
causes.
So now we're talking about how much damage do we get, which is obviously going to be because of these 2 things, caused by these 2 things. So this little graphic pretty much shows that this poor little girl with the flower, I don't know why she has a flower, but she's shaking for sure. So you have the magnitude here, and this is the energy released from the source right here. And that's the focus right here, right? So it's earthquakes that are small in magnitude and far from urban areas or barely felt, but they're recorded on seismographs. Remember when we looked at that graph just a little bit ago as we were wrapping up lab, and it showed all those little tiny earthquakes everywhere. And we're like, geez, these people must be shaking all the time. They probably don't even feel those itty bitty ones. Those ones that are like a 1, rated like a 1 on the Richter or less than 1. They probably don't even know it happened, but the seismographs do because they're very sensitive. So then you got your intensity, and this measures like you're shaking, right? And your like it depends on the depth of the focus, how far down it is. So think about it. If your focus is really, really, really deep, as opposed to your focus being more shallow, that's obviously going to impact how you feel it, how much damage is caused. So earthquakes that are shallow and near urban areas are greatly felt, even if they're weak. All right, so here's your Richter scale. Just one of many ways to measure earthquakes. When you guys got reading this chapter, did you realize there were so many different scales? Usually Richter's the one you hear, but it's interesting. If you, yeah, there's a bunch of them. So if you were to watch news coverage when there's an earthquake, they'll say this earthquake was a 4.5. And sometimes they bother to tell you what scale they're using, and other times they don't. But if they don't bother to tell you, they're implying that it's Richter scale. So this dude, Charles Richter, is a numerical rating system for measuring earthquake magnitude based on the largest wave's amplitude. And each number is a magnitude of 10 greater than the one before it. So this is kind of metrics. This is pretty basic here. So if you've got something that's 0 to almost 2, you don't feel it. So if you think back to that map, they didn't feel any of those.
What does it say at the bottom where it's purple?
It says insignificant.
Okay.
That's hard to see on that. It's a little more visible on my screen. It's probably a brightness thing. So then you may see some swing in here between a 2 and a 3. 3, you've got your comparable vibrations to a passing truck. So if you've ever stood on the sidewalk and they don't mean like a Ford F-150, they mean like a semi. You can feel that, right? Bounces the ground a little bit. And then when you get in the 4 and 5, you've got stuff that falls off shelves and little windows that break or whatever. And then this is when it starts to get real scary, when you get in the 4, 5, 6 range. So now you got furniture scooting around, chunks of plaster falling off of walls. I don't want to see plaster falling off of walls. That sounds terrifying to me. And then when you get into the 7, this is when you get damage to big structures that are well built. And then the 7 to 8, you get big cracks in the road and whatever. And the 8 and the 9, you get bridges that fall apart. And 9 and over, you got total destruction here. This is apocalyptic. Yes, Milo.
Love how it says like outstanding.
Right?
Extraordinary.
That wave was outstanding. That wave was extraordinary. Potential hazard, extraordinary.
Like, it's fun. No, my house is like completely destroyed. That was outstanding.
But it was outstanding, right? I love stuff like that. Oh yeah? Where were they when so he said his grandma and grandpa lived through an earthquake. Where were they? Whoa, their whole house collapsed?
Yeah.
Where were they when where were they?
Somewhere in
South US, or they were in the US? India. Okay, so somewhere in India, South India. Yep. Okay. So then you've also got, yeah. So this one, you got your moment magnitude scale. Yeah. So this one is a little, it's not outstanding. I don't see outstanding or extraordinary here, but this is one geologists use a lot. Okay. And it considers energy release, size of fault rupture, amount of fault rupture. So this kind of scale this is like, you ever hear doctors talk to each other and you're sitting there like, what the heck are they saying? It's almost like they're speaking in code. Or engineers, they're worse. They're worse. So that's what you got here. This is like experts speak to another expert. This one's moment magnitude. Yeah. Now, when you're talking Richter, that's more like doctor, scientist, whatever, speaking to laypersons in a way you can understand. You understand extraordinary and outstanding, right? I mean, you know what that means as opposed to some of this stuff. This is more industry speak, right? And then lastly, we have this modified Mercalli. So this is Roman numerals, just so to confuse everyone. And then there, by the way, what do we use? We don't use Roman numerals. What are our symbols and letters? What do we call it? Say it again. Arabic. We write in Arabic, which is really funny because there's some great memes of posts for people that are like, why are we writing in Arabic? Like they think it's bad because it's great. So those are good. Those are real good. So yeah, here's where you got instrumental. We understand instrumental. In this case, it doesn't mean like, oh, it was instrumental in making our day better. It means that, you don't feel it. Only the instruments do. And then just perceptible. These are maybe a little more nuanced, shall we say, than Richter.
Yeah, I see no outstanding.
Yeah, catastrophic is maybe a better way to describe it rather than outstanding and extraordinary.
It's like pure black.
Right, yeah.
Fine.
These make more sense, like if you read the words. Like, I know what rather strong means, but that was an outstanding earthquake. Makes it sound like it was a fun day, whereas these really describe what's going on. So how do you locate the earthquake? So your distance and time of the earthquake. When you have distance and time, you have a curve called a what? We said it before.
Travel.
Travel and time. There you go. Time travel, drop
Yeah,
time.
travel.
Time travel.
Time trouble.
Yep. 1.21. Anyway, so you need a flux capacitor for that. So this is determined using those data, get those curves, right? And then areas where seismic activity is more common and often near plate boundaries. What do we call these areas? All these red areas. Do we know? Close. That would be volcanoes, but yep, same idea. No.
Quake spots?
Quake spot.
I'm going to give you a clue. There's a little part of the US right here that kind of comes across like a little vertical strap that tends to be real religious, and there's a nickname for it. What's that?
Bible line?
Not line, Bible Belt. Okay, so if that's a Bible Belt, what do you suppose these are? Seismic belts. Oh, I love it. Good job. Seismic belts. Okay, so these are areas where you've got lots of seismic activity. What do you notice going on along these areas? Look at the blue lines. Ah, yep, they're all plate boundaries. See the blue lines? And you can probably tell whether these boundaries are convergent, divergent, or transform based on the number of earthquakes you see, right? Look right here down the middle. What kind of boundary is this right here? You should all know it.
Divergent.
It's divergent, right? Seafloor spreading. Ton of earthquakes or not too many?
Not too many.
Yeah.
Why is it? I don't even see that much earthquakes in the African.
Yeah, there's not a lot because look, most of this African continent is on this plate and there's only a little bit right here. So that probably tells you something. Right here, you've got some transform activity for sure, right? And look through here. Good gracious. And what's this area called? We all know it.
Hurricane Alley.
Not Hurricane Alley.
Hurricane Alley.
It has to do with the volcanoes. We talked about it last week. This is Ring of Fire. Okay. And look at Ring of Fire and the seismic activity. Good gracious. Japan. Where's Japan? Right around here? I can't even see Japan.
Japan. But I love Japan.
Or Japan,
I love Japan.
which is interesting because do you guys remember what was it? Fujikima? There's a nuclear power plant. And there was this place has all kinds of issues with tsunamis and everything else. And that would be
Or Nintendo.
Because heat will trigger the nuclear.
yeah. So earthquake hazards. So what are some hazards of an earthquake? What can happen? All right, Drew, you give me one.
Making and like bridge collapsing and
Okay, bridge is collapsing. Wait a minute, give me one. Bailey, give me a different one.
buildings collapsing.
Yeah, wait a minute. Sky, you got one? What's something that an earthquake can cause?
Like,
Roads breaking apart. Good. Okay, so we got lots of them here. All right. So we're talking about structural failures. That's a big deal too. So your earthquake hazards determine the severity and damage, obviously. And then you've got structural failure, elasticity of materials and the height of the buildings, and resonant frequency, which we're going to talk about in a minute, which is actually really cool. So San Francisco, 1989, was the world's first highly televised earthquake. I remember this one. I was in middle school. I think I was in like 6th grade, junior high, right? So no, 7th grade, junior high. This is a double-decker highway.
Oh.
Okay. And there were people in the cars because it was around rush hour, but it was also the World Series. So most people got out of work early and went home. And if it weren't for that, this would have been bumper to bumper traffic when it occurred. And those, what do we call this when one structure falls on top of the other? Do you know?
Pancakes.
That is exactly what happened here was pancaking. And every single car in there would have been pancaked and all of their occupants.
Got one truck that's.
Yeah,
Without-
this car right here is like, oh, you know?
Like, this is the sign I can
For
find.
real, yeah, for real. He's like, apparently I'm supposed to do something with my life because this is crazy. Yeah, I remember this vividly. It was a big deal. I was actually babysitting the little boy across the street when it happened, and you know, everybody was freaked out about it. Like it was all over the news for days because it was really serious. And I got 2 quick videos about it. So what you can say?
I remember watching like a baseball documentary.
Mhm.
and It was like this guy was on the big light
Yeah,
and it was just
yeah. That probably is this one. So there's some coverage here about it. And because it happened when people had all of their media cameras, you guys get back there, all the media cameras were set for the World Series. They were all like, oh, let's film San Francisco because there's a World Series here today. Let's get footage of the city. So because of that, it got captured on camera and it was pretty wild. Oh, I turned the volume all the way down for that last dude. Let me put it back up.
Got to witness a huge hit. And I'm not talking about. It was October 17th. Just-
What is going on there?
There's still another video playing in the back.
Okay, hold on a second, because that is crazy. Wait a minute. What
What
is this? I'm not talking to you. What is that? I didn't even open that. That is bizarre. Hold on. Sorry, that was weirdness. Oh no.
That was.
Where's my guy?
Video weird.
Where's my dude? Yeah, that was very bizarre, but we weren't even in YouTube, so I don't know why I did that, but okay. Okay, go here and go here. I'm having tech issues today. Fun day. Yeah, the gremlins. It's always the gremlins.
It's the corporate spies.
It could be.
Watching you from your laptop.
So this one's a little History Channel blurb, but it's interesting.
Baseball fans in the fall of 1989 got to witness a huge hit. And I'm not talking about a triple with the bases loaded. It was October 17th, just half an hour before Game 3 of the World Series was set to begin in San Francisco's Candlestick Park. The ground began to leave. The television feed flickered, then went out. Then all hell broke loose. When the broadcast resumed several minutes later, the announcers were visibly and literally shaken. The Bay Area just experienced a massive earthquake. Geologists estimate it had a magnitude of 6.9. It caused landslides, walls and buildings collapsed, rubble fell, fires started. The quake's epicenter was in the Sierra Mountains, near Loma Prieta Peak, some 16 miles from San Francisco. Sometimes called the Loma Prieta or San Francisco-Oakland earthquake. It's also referred to as the World Series earthquake. It was the first major earthquake in the United States to be broadcast live on TV. The Bay Area hadn't seen a seismic event like that since the Great San Francisco earthquake of 1906. That earlier earthquake, an estimated 8.3 on the Richter scale, nearly destroyed the city. It caused massive fires and killed over 3,000 people. Compared to that, 1989 was a hiccup, but a devastating one nonetheless. Over 60 people were killed and several thousand were injured. 42 of those fatalities happened on the Cypress Street Viaduct on the Nimitz Freeway in Oakland. The upper level of the road collapsed, crushing cars below. It's also estimated that the quake caused over $6 billion in damage. Despite all
In
the
1989.
destruction, it could have been much worse. And Bay Area residents may have our national pastime to thank for saving their lives. You see, both teams in the World Series, the Oakland A's and the San Francisco Giants, were from the Bay Area. No place in the country was more invested in the game. The ball game was going to start 5:30 p.m. Pacific Coast time. That's usually Russia. But because of the series, many Bay Area baseball fans were already settled in to watch the game and cheer on their teams. That meant they weren't out in the streets or on the roads when the quake hit just after 5 p.m. Thanks, baseball. The World Series finally resumed 10 days later, on October 27th. Several first responders were honored before the game and helped throw out the first pitch. By the way, the Oakland A's swept the series in 4 games, thanks to 2 commanding starts by pitcher Dave Stewart and strong offensive performances from Ricky Henderson, Carney Lansford, Dave Henderson, and Jose Canseco. The A's broke the tradition by not celebrating their win with champagne, a solemn nod to those who had been hurt or killed in the quake.
Once again, I found that sound driver.
No,
Getting elected
60
president.
people were.
dead.
And this is another interesting one. This is the same earthquake
Similar to that.
in a classroom.
Idea.
At 5:04 p.m., American Studies 1 was underway at UC Santa Cruz.
No one's tired anymore, no?
Look at the lights. Mhm.
They're like,
No, these are all like security cameras. And this wasn't, that wasn't, this is a security camera in a store.
It was everywhere. This was the most visible earthquake ever.
Now that's what the Roblox. Now that's a smart baby. That baby's going places. That baby's like, "Here's the back."
You think we can thank the cameraman?
Right. So the late 80s. The late 80s and early 90s. The late 80s and early 90s were really the beginning of security cameras. And you saw how those people looked, right? So, you know, and you try to catch a criminal like that. Can't tell what anybody is. That's so grainy and terrible. But that was the beginning of that sort of surveillance. So because of that, we had the opportunity to see what was happening inside of buildings, inside of classrooms. Not fun. I don't want to do it. So resonant frequency. All right. I love this topic because it's super interesting. And this comes up again in physical science. Okay. Yeah. You know this one, right? So resonant frequency, without resonance, we don't have music. We don't have voices. The whole world would be see-through and greenhouse effect would be impossible. So resonance is a way of storing energy by vibrating at a particular frequency, and everything in the universe can resonate. So kid on swing, you've done this with a kid on a swing, or you've been the kid on the swing. When the swing comes back and they say, push me higher, and you push them, there's a certain point where if you push them just right, you get the most energy, right? It depends on where they are. Like if they're coming at you, you step in here and push them, they're only gonna go a little way. If you wait till they get here and then you push them, you get the most energy out of that swing. So kids get higher and higher as you push them. So it's a fundamental law of playground, right? But it sums up the basics of resonance. If energy is added to something at its resonant frequency, it can store more and more of that energy by vibrating at that resonant frequency, and it means it's resonating. So there's a glass and they're sending sound waves at it, and sooner or later it will just crack.
It looks like Jello or something like.
It does. See the way it moves? And you think of glass as brittle, but it's not.
Video on homework.
Oh, yeah. So you can do this too. If you have nice crystal in your house, especially, it doesn't really work with cheap wine glasses, a little bit, but better with crystal. But if you hum into it or whoo, you can hear it kind of back at you.
And you can hear it click it whenever.
That's the pitch. Another thing that you may have done, my family used to do this at like every Christmas and Thanksgiving, but when the crystal was out, you dip your finger in the glass and you hold it down there on the base, then you run your finger around the top of it and you'll get just right and it'll hum. You see people that make make glasses sing, that can make songs out of. Benjamin Franklin actually had a big old thing that did that. It's pretty cool, right? So we have a friend who was actually our former gymnastics coach, who was an architect, and he told a story once about way down where the Georgia World Congress Center is now. There was an Omni and a bunch of stuff down there. It used to be a spot where a lot of people would go for the night out. Okay. And he got a call. He and I guess a crew he was working with, I think at the time, or maybe it was when he was in school. I'm not sure. But they got a call because there was a band playing and people were dancing. And everybody was like stomping and dancing to the beat. And then suddenly the whole floor did this, right? Soldiers marching on a bridge. If they're marching in step, when they get to the bridge, they stop marching in step. There's a reason for that. Okay, so it's really interesting. The best known example is a particular bridge, which I'm going to show you. But these two give you an idea. Put these side by side so you can see them. But these are shake tables. Okay. And if you watch the little weight on top, it takes a little while. No, these are shake tables, but what they're showing is different wavelengths and different, so there's hertz, that's how we measure waves. If you look at where that one's going, this one's going a little faster than the other one, obviously, but the other one will get there. But it's still shaking. You see now it's not, look at that, it kind of stopped for a minute. The table's still shaking, but the structure's not shaking. And if you watch that one there on the left side of the screen, The tall one's starting to go, but the short ones are not. That was really good. I mean, it's really, really shaking now. It's like wiggling, like doing this kind of deal. And if you look at the one on the right, the bottom one is shaking more than the top two. Now the top one, and now they're all going, see? It reminds me of those blow up things they put outside of like a car dealership. Those people, that little man does this. That's what it looks like, right? But now look at the one on the left. The big one is slowing down and the middle one is picking up. And all they're doing is increasing the frequency of the waves on these shake tables. Whereas the one on the right now is pretty much almost still. That one stopped. See, that middle one is now super going and the other ones are now relatively still. But these are examples of like how resonant frequency is important when you're building something. No, they don't ever fly off, which is great, but still. Like that big one is almost still, and the bottom one still hasn't gone anywhere, but that middle one is really going, right? And if you watch, if I can move it along a little bit, move it ahead a little bit, now we've got the little one going. And now the little one's slowing down again. So it's interesting to see how the placement of the weight from the source of the wave is changing. This is the most famous one. Okay, this one was also recorded. Now, this wasn't live TV because we are back in the day, but this was one of those newsreels. You know, those ones where it's like, tonight there was an amazing, and it's always funny. They always have like music playing in the background. They used to show them in movie theaters, right? They're really dramatic. So the Tacoma Narrows Bridge, this is probably the most well-known example, and it's kind of crazy.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million.
Everybody spoke like this.
But it's thought to overtake the Great Fund. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
I love the music. It's outstanding, yeah.
Only 35 miles an hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing.
So did you hear what he said? What's causing the shaking? Wind. It's just wind. Run, dude, run. Wait, listen.
And plunge into the water below.
Oh.
Fortunately, the only casualties were a car stalled on the bridge and a dog.
A dog. He said it so plainly too. Fortunately, the only casualties were the car and the dog. You're like, what? What?
Dare you?
It's just a dog. So that, yeah, it's just, yeah. Oh, there goes my car. You know what I mean?
Get a new one.
So this stuff, this topic will be covered again, obviously, when we get to physical science, because we talk a lot about wave theory and function. But that bridge, there was no earthquake. That was just wind. The wind was hitting it at the right frequency. Wow. And they called it Galloping Gertie after that, because yeah, it kind of galloped all right. And it was the world's third largest suspension bridge. And it was not old, it was relatively new. Like, ta-da, look at this bridge. We're gonna show everybody the bridge. And then there goes the bridge. So, so those are structural failures. All right, now then we have things like land and soil failure. So what is it called when you get areas where your groundwater is soaked, your soil is really wet, and then your soil begins to act like liquid? Who knows? Caitlin, you know? Like, yeah, this was liquefaction, but yes. And it looks like liquefaction. So Oh, it didn't go away, but that's what it is. This is crazy. This is a dude in Japan, okay? I think he's some American guy, and I'm not sure what he's doing there. I think he's there as a student or on business or whatever, but he's super casual as he strolls around the park and whatever, and shows you how the earth is just turned to like quicksand goo. I mean, he's really relaxed about it. He's like, oh yeah, look at those girls over there. I mean, it's really strange, but
See the cracks moving?
There was another dog.
that's a sidewalk. Yeah, another dog.
That crack was not there.
That crack was not there.
Yeah, okay.
The dog is
Oh,
like,
Earth
dude,
is
danger.
moving. I felt like I was drunk.
I mean, you
See,
probably
different
had
parts.
sake, but I.
Wait, the watch though, this is interesting. Look,
There's water just coming around.
Wow.
Feels like a skin. Like, oh,
Yeah.
there's water. The ground.
look, you can see it. You see it?
Ground is just swaying right now.
It's like, go.
Yeah, danger. Why do you have me out here? I don't like.
Getting bigger and smaller, going back and forth. And there's water coming up all over in the park right now.
Look at it. Look, see that?
Wow.
Oh no, I'm out of there.
Moving.
Stick your hands in it like that.
Water, I don't know, water lines
No,
are broken.
Look at this. And now these girls just
Water's
like
not there.
sit on a blanket picnicking like nothing's going on. It's really weird.
Coming up, different places. Here, it's coming up the sidewalk.
That water line or water?
It's groundwater. Look at it.
Buildings were making a racket.
You're
My
way
serious,
too
but I was sick first, because I didn't know what was going on. I could just feel. I was going,
Did he do this?
up over another crap.
He do this?
Very disorienting. Yeah. I mean, he's the most chill
Why is the
dude.
trains are not running anymore? I was like,
Trains are out running. No big deal.
we've got a little lake. Here's a huge crack.
Look,
It's still moving.
look, you can see it. See it?
Put your hand in.
No, no.
It's going back and forth, swaying.
Pop your phone in, let's see what's going on.
I'm kind of nervous.
Not sound nervous.
This is reclaimed land that I'm on right now. This used to be part of Tokyo Bay. And they created this land by throwing landfill or mountains, rocks out here. And so this land could just go potentially. I don't
He
know.
did this as a bit. He's like, hey, look up.
I don't know what.
Quite a few people in the park. They don't seem to, or they're not running away. Park, rural. Park.
Sombrero.
Those on Scottsburg ended.
You see the girls on the blanket at the beginning that were just on a tree, under a tree. They're just down, never mind. The earth's moving. It's all good. So that's soil liquefaction. What do you call these giant waves that are caused by this vertical movement of the ocean floor? Wait, Parker, you tell me. You haven't told me anything yet. What do you call the big waves? Yeah. All right, there you go. He's awake. Tsunami. Okay. There was a terrible tsunami not that long ago. Do y'all remember it?
Yes.
You were alive for it. It's this one here, and it's insane. Big wave. Indonesia. That is insane. It's a plane. This is video from an airplane or a helicopter.
Wow.
That's soil liquefaction.
That's scary.
That is insanity. Look at that.
Looks like some Dr. Strange stuff, just like working.
Yes.
Mhm. So this was filmed like a day or two after. And they said 5,000 people were missing and there were like, what, 1,944 people they believe dead?
And I could triple.
Yeah, so this is called the Boxing Day tsunami. It was on the 26th of December, 2004. So any of you alive? Nobody, actually nobody in this room was alive yet. Oh, that's right. My last class, there were people alive, but not you. Okay, so this was a 7.5, at 7:58:53 local time, and this is in Indonesia. An earthquake with a magnitude of somewhere between 9.1 and 9.3, that's Richter, struck with an epicenter off the west coast of southern Sumatra, Indonesia. What's the big industry in Sumatra, do you know? Tigers. You ever been to Starbucks? They do a lot of coffee in Sumatra. It's very agricultural. That's why when you saw that time lapse, there were a lot of like fields and stuff. Okay, so the earthquake was the third largest ever recorded, ever, right? Based on seismographic measurements, and the largest in the 21st century, and had the longest duration of faulting ever observed, between 8 and 10 minutes. Usually it's like, you know, a minute, maybe less than a minute. This was a couple minutes at most. 8 to 10 minutes is a lot of faulting. That's huge. And it says, blah, 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 we're gonna lose my spot. It caused the planet to vibrate as much as 10 millimeters and also remotely triggered earthquakes as far away as Alaska. Indonesia is nowhere near Alaska. These waves went all the way through the planet where they could. Obviously, they can't get around like the core, but around things, they went all the way down. So the earthquake produced waves up to 30 meters, which is 100 feet high. About how high do you think we are off the ground here? No, right here, from here to the ground. Yeah, like if you're on the deck, 20-ish. Okay, multiply that times 5. That's a wave coming at you. Not fun. And it devastated communities along the surrounding coast of the Indian Ocean, killing an estimated 227,898 people in 14 countries. It's one of the deadliest natural disasters in recorded history. They started with, oh, we think 2,000 people are dead and 5,000 are missing. It's
227,000.
almost 250,000 people. That's massive. Yes. So there's a lot of little tiny, yeah, like if you look, yeah, there are little itty bitties around Indonesia. So Indonesia is where, right? Here-ish, right? Here. There's lots of little places through here, but then all of these areas around it experience issues as well. And then of course it came all the way through the planet. Sorry, lovely. Over here, all of this, and then it came all the way through the planet, all the way over to Alaska. That's a long way. That's from, you know, here to there. The difference, that's a lot, right? This thing was huge. It was absolutely huge. And it's Boxing Day. What's Boxing Day? Does
It's the
anybody
day
know?
after Christmas.
Yeah, why is it called Boxing Day?
You get rid of all your boxes.
That's right, you box stuff up. That's what it's called. That's usually what the British call it. And I remember I was at my in-laws' house because we'd been there for Christmas. Actually, I was pregnant with Cole. So none of y'all were born. I was pregnant with Cole. And it was terrifying. Like the news was just absolutely terrifying. It was clip after clip after clip of like those people were filming from like hotel balconies, right? Clip after clip after clip of that. There are some videos you can see where like there's little like alleyways between buildings where it's flooded up multiple stories of the buildings and there's cars, poor people hanging on cars. It was catastrophic for the whole planet. Actually, the whole planet vibrates basically a centimeter. That's a big old deal, right? So how do we forecast these things? What is the term we use to describe the greater probability near seismic belts? Do we know what that is? Anybody? I'm gonna give it to you. That's your seismic risk. Think back to lab. Seismic risk is definitely going to impact how much you pay for.
Sure.
Oh, insurance, talking about insurance again in science class. Why all this economic stuff? Well, because it matters, right? So occurs at regular intervals. What's the word we use here? Do we know? Yusuf, what you got? Recurrence rate, right? So recurrence versus occurrence, what's the difference? Let's think about it.
V means again.
Yeah, I was gonna say Milo, what were you gonna say? Yeah.
I was gonna say that V means like.
Mhm. Again, correct, right? So occurrence, something happens. Recurrence, it happens again and again. So what do we call the areas along active fault belts that have no recent seismic activity, Bailey? There you go, seismic gaps. Okay, so they're on a fault, but, and then what's this last one gonna be, Yusuf? The rate at which stress builds? There you go. Okay, stress accumulation, that makes perfect sense, right? The rate at which stress builds. All right, so I'm gonna recommend this one to you. This is on Netflix right now. I haven't had a chance to watch the whole thing yet, but Jason started it the other morning and he was like, this is incredible. So it's TVMA because, you know, I think people die and there may be a little language, so keep, no. So if you're not allowed to watch TVMA, sorry, but if you are, I recommend it. What now? Mature audiences. So like movies have the ratings like G, PG-13, R, NC-17, X, all those ratings, right? But TV has different ones. They have like MA and
TV
14. Yeah. What were you gonna say?
Me and my friend watched like 4 movies that were like 18 plus. So
Yeah. So I'm like I said, I haven't had the chance to go through the whole thing. I believe it's TVMA because there is actual death and destruction because it actually happened. So it's yeah, so it's actually it's described as a historical documentary. So it's not a movie for a movie's sake. It is actual documentary. And it says survivors' firsthand accounts and actual footage fuel this emotional docuseries about the deadly 2015 earthquake that shook Nepal. What's this in the background?
Mount Everest.
Okay, Mount Everest is in Nepal. All right, so if you have, Mount Everest is covered in ice and snow. And people have little tiny, there are camps on the way. Yeah, like, you're right, there are dead bodies. Right, yeah. So what they do if you want to climb Mount Everest is, you go to the first base camp and you hang out there for a while and you go to the next one. And sometimes you do a little back and forth between. You don't just go straight up Mount Everest. Aside from it taking forever, why can't you just do that?
change in pressure.
That's a girl. Yeah, it is not something your body can deal with. So you have to do it gradually. So there are encampments all over Everest, and they are in the easiest path up. So think about what an earthquake would do. Wow, you know weird stuff, Andrew. That's
Yeah, it takes like.
okay. I have a friend in Michigan who's a physician, and she does a dip in frozen Lake Huron every year for charity. But I figure she's a doctor. She knows if it's gonna kill or not, but that's ridiculous. So what were you gonna say, you said? Yeah, they're called crags and crevasses, right?
Big guy with what kind of stuff?
Ooh.
Legend.
Oh, like a Yeti? Yeah, that's like a Himalayan legend. But they have these big, think about it now, these big crevasses, which are basically giant cracks in the ice. And they put ladders over them. And people that are hiking have to walk the ladder over this, it's just a ladder, like the kind of, aluminum ones you lean against the house. It's just like that. And they walk on across it, and they practice doing it on smaller ones before they do big ones. And imagine what an earthquake would do in a situation like that, where you've got massive cracks, people are up high, people are down low, you have to take this path to get to them. And now the path isn't there. So it's a huge deal. And what else would happen in a place like this if it starts shaking?
I'm gonna say helicopters can't reach them.
Right? Helicopters can't get you. What were you gonna say? Yeah.
Avalanche.
Avalanche. Oh yeah. So if you're at the top and you get stuck, because your way down has been completely shattered.
Then you might as well just die.
Yeah, and if you're at the bottom, everything that's on top of you is coming down, because if you think about it, all those camps going up the mountain are in, like I said, the easiest path up. So if it's the easiest path up, it's also the easiest path down for everything coming down. Not fun. So recommended. Yeah, but if you've got stuff that starts tumbling, a lot of it, you're right, a lot of it will come the steepest path. That's absolutely true. But if you've got like rocks and stuff, if they're gonna, the difference is if they go down the steepest path, they're gonna like kind of bounce off on their way down. But if they're going down the easiest path, they're gonna roll that whole way through. And it's like almost like a little valley in certain places where they have encampments. So if you're allowed to watch TVMA, like I said, I haven't watched it myself, but I asked Jason, I said, would it be okay for my students? He's like, yes, it's awesome. So, all right, here are your answers. I'll leave these up for just a second and I'll switch to the next one. And then next week, we're back, same thing. I noticed a lot of you had not done your homework when I checked last night. Some of you had already done it. Some of you had not done it yet. So if you haven't done it yet, it's going to be difficult because remember, you're supposed to give me information that somebody didn't already get about Harry R. Truman. So the information we do have about Harry R. Truman, let me see. Who has posted something since then? I haven't checked. All right, what did you say?
I posted that he didn't know his middle name, but on his World War II registration thing, I think it said Rain.
Okay, all right. What did you have, Bailey? Yeah, what did you post? Do you remember?
No, he got honorably discharged when his boat was something by a German.
Very interesting. Okay, Caitlin.
He was a bootlegger.
He would have fit in well around here. Uh-huh.
He served 10 under Group 7 in the World War.
Okay, that's interesting. So now what's the big deal? Why did I tell you to look him up? Like, why is he even a thing, Milo?
The pool.
Wait a minute, who's saying it? Mount St. Helens, yep. Because what was different about him from everybody else in the area? Piper.
He stayed when the election happened.
Yep, he refused to leave. I've been here my whole life, nothing big has happened. And the odd thing is, that's exactly what my grandfather used to say when they lived 4 blocks off the oceanfront and every hurricane came in and they're like, everybody within, a mile of the oceanfront needs to evacuate, come in. Everybody in Sandbridge needs to come. And my grandparents, from my grandmother, until they built the Ramada Hotel, could look out her bedroom window and see far out into the ocean. That's how close they were. Every hurricane. I'm not going anywhere. So very much, I get where this man comes from. All right. So you all good? Now I have little cups for you to put your candy in now. I'll get them out for you because I noticed people were like using the bigger cups. So I got you this candy cup.
If there's like a tornado.
Dang, that's big. Hang it all, get the barn. Get the barn. I'll get it.
I
Here,
bet that
candy
is,
cups for candy.
that's most likely there.
Knock yourselves out.
A hurricane. Get
Right, Miss
behind it.
Lily?
Come at it.
Catch you later, Miss
Go away.
Lily.
Bye.
Alex, bye.
All right, we can have my voice.
Because Alex